Yep.
Okay. I want to welcome everyone to my lecture today. But before I get started today, I got some few announcement to make. I want to tell you, if you look at the syllabus, I said if I give out 7 assignment, the assignment with the lowest score will be dropped. But now that I gave 6 assignment, okay, I'm still going to drop the assignment with the lowest score. Okay, I'm still going to drop assignment with the lowest score at the end of the day. And I also want to use this opportunity to tell everyone that the final exam is actually going to be cumulative. So later today, I'm actually going to release some practice questions for the final later today. And I also want to remind you that it is a time that students are required to complete student rating, okay, of professors. So the university is expecting that. You can go to the Canvas page and do that. Okay, I want to welcome everyone to my lecture today. The other time, yesterday, I started what I call time series analysis. And of course, we're going to continue from where we stopped. I told you I was going to start from the material for yesterday. This is actually where we stopped yesterday. We actually stopped at, we were given a model, an autoregressive model of that one. Okay. And given the autoregressive model of that one, we've been able to obtain the mean of the time series variable. We've also obtained the variance. But what we want to do now is actually to obtain the autocorrelation at different lag. Okay. And to remind you, this is an autoregressive model of that one, as it contains both the signal part and the noise part. The signal part is actually the deterministic part. Okay, why this is a noise part. Okay, so what we actually want to do is at lag 1, we want to find the autocorrelation. Okay, we want to find the correlation between the two time series variable that is one lag apart. Okay, and this is how you're going to do that. The YT here is actually this, right? That is this. Okay, so that is why you see that YT. I wrote the whole of that. Then you're going to write YT minus 1, which is this guy here. Okay, now you want to find the correlation, of that. But I want to tell you the correlation here. Okay, you can only find, the correlation of this guy here. Okay, the correlation will only attract the variable. Okay, so the correlation of a constant, is 0. That is going to go away. Okay, and that was why you have that. This can also be written as this. Okay, the constant is no longer, it's going to be part of that. Okay, take a look at that. Okay, so if you take a look at what I have here, this is giving us two things. We can find correlation between, this guy, okay, and this guy, which is this one. And we can also find the correlation between this guy, okay, and this guy. Look at that. That's what we have here. Okay, so take a look at that right now. Okay, so what I'm trying to say, when you have something like this, and it is the same thing as, okay, you want to find the correlation between this guy, okay, and this guy, is this one here, right? And the correlation between this guy and, it's more or less like you are using the whole of this to multiply this, okay, in a way, and you're now finding the correlation of that. Okay, now Excuse me. Now, okay, the correlation between the same variable is one. Of course, like the correlation between me
Sorry,
and
you cut out there for a second. Do you
oh,
mind repeating?
okay, okay, sorry
Okay.
about that. Okay, you hear me now? You can
Yep,
hear
I
me
can
now,
hear you
right?
now.
Yep.
Mm-hmm.
Oh, okay. So I'm gonna go back right here. We actually want to find the correlation at like one. Okay, the correlation between YT and YT minus one. Of course, what is the YT? That is the model that we're giving. We're gonna put the whole of this. That's all you have right now. Okay, comma YT minus one. Okay, so because it's a constant, it's gonna go away, right? And we're only gonna have the correlation between this guy here and this guy here, which is this one, right? Take a look at that. And right now, you know, with what I'm seeing here, I'm gonna find the correlation between this guy and this guy, which is this one. There's the correlation between this guy and this guy, which is this one. Can you see that now? Okay, now this is a constant, 0.9. It's actually gonna come out. Okay, it's gonna come out. So we have 0.9. Then we're gonna have the correlation between YT minus one and YT minus one. Take a look at that. What is the correlation? These are the same variable, right? It's just like if I want to find the correlation between me and me, of course I'm going to be perfectly correlated with myself. Okay, and that is going to be one. Okay, the correlation between the same variable is going to be one. Okay, and you know what? The correlation, if you take a look at this guy here, okay, we have made an assumption from this is from assumption that, okay, you know what, the correlation between a noise, okay, and you know, time series variable should be zero. Okay, because if you take a look at this is a predictor. I think you know that in this model, YT minus one is a predictor. And we're trying to say there shouldn't be any correlation between a predictor and a noise. Okay, and that is the reason why that is actually going to be zero. Okay, it's part of the assumption. Okay, I'm going to say that again. Correlation between predictor and a noise have to be zero. That's an assumption. And that was why the correlation is going to be zero and zero plus, and that was why we get is 0.9. So 0.9 is actually the autocorrelation at like one. And that is confirming what we have here. That's confirming what we have here. Because 0.9 here is just the contribution of the previous the immediate value of a time series, okay, the contribution to the current value. Okay, that's what we just confirmed right here. Okay, now that is a 0.9. And so if it's 0.9, it's actually the correlation. Give me 1 second. I want to clear this. Why is it not? Okay, gonna do something now. I'm gonna stop my share. Then I'm gonna reshare again. Okay, now I've been able to obtain the correlation at like one. Okay, now let's now go and obtain the correlation at like two. Okay, correlation at lag 2. Of course, at lag 2, two lag apart. You're like, what is the correlation between the current value of the series, okay, and uh pass, like, it's not immediate pass, but immediate pass. Like I'm talking about, if I'm talking about daily, then I'm talking, if this is it for today, okay, today is Wednesday, right? I'm talking about this guy is actually going to be Monday. Okay. Now, once again, what is YT? That is the model, right? Okay. The model that you are giving, YT. Okay. And YT minus 2 is this guy here, right? Then we're going to do the same that we did the other time. Correlation for that, the constant is going to go away, right? We're going to be left with just this guy and this guy. That's what we have here, right? Okay. Now, we're going to do the same that we did the other time. That was okay. We want to find, you know, the correlation between this guy and this guy. Okay. is what that's why I wrote this. Then the correlation between this guy here and this guy. And let me tell you this, assumption again, you know, YT minus 2 is also going to be a predictor because it's a pass. It's also a predictor. So the correlation between a noise, okay, a noise is like a shock, a current shock on the system, okay. So the correlation between the two should be 0, okay, under assumption, okay. Now what are we having now? Okay, now we want to look at the correlation, you know, between this now. Okay. Now we look at what we're going to do. We're going to take a caution. Okay. From here. Now, YT minus 2. This is YT minus 2, right? Okay. Now 0 0.9. This is 0 0.9. Now we want to rewrite a model to reflect YT minus 1. How are we going to do it? Now let's recall. What was the model? It was initial model was YT. Okay. Equal 0 0.8 plus 0 0.9, okay, YT minus 1, okay, plus WT. Now, if I want to curate, I want to find YT minus 1, okay, based on this model, I'm still going to have 0 0.8 plus 0 0.9, okay, but this guy is going to be YT minus 2, and this guy is going to be WT minus 1. Look at that. Okay, I'm using the knowledge of this to rewrite the YT minus 1 because if YT can be expressed, the current value can be expressed as immediate past, then the immediate past can also be expressed as, past. Okay, I'm going to give an example now. If this guy is Wednesday, let's say this is the price of a commodity on Wednesday. Today is Wednesday, and it's a function of, the price yesterday, right? Yesterday was Tuesday, right? What if I want to make yesterday to be a response? I can also relate yesterday as a function of the immediate past to yesterday. That's what I have. So if you take a look at YT minus 1 here, okay, I'm going to write the whole of this to represent YT minus 1. It's more or less like subtracting 1 from T, subtracting 1 here, subtracting 1 here, automatically going to give me this. And that is why what I'm trying to tell you now, YT minus 1 is now the whole of this. Look at that. It's now the whole of that. Okay? If it is the whole of that, you know what I'm going to do? Okay? Now, I'm going to use this guy, don't forget the 0 0.9 here, to multiply everything. So if I want to do that, and if I use this to multiply this, 0 0.9 times 0 0.8, that would be 0 0.72, which is a constant, right? Okay, 0 0.9, we multiply this, okay, and the 0 0.9 we multiply this. But you know what, when I want to take the correlation, because the constant is going to go away, okay, I'm only going to be left with 0 0.9 on this one, then 0 0.9 on that one, and that is how I got this. Okay, and I still have my YT minus 2. Now let me ask a question. Do you understand it up to this junction now? I need you to comment if you understand it up to that junction, or you say yes, or you comment yes. Did you understand my explanation? Can you guys confirm again if you are still hearing me clearly?
Yep.
Yes.
Okay, so I need you to comment or comment yes or say yes if you understand my explanation to this junction, and if you need clarification, you tell me right away.
Can you clarify where you got YT or the value for
Okay, you
YT
want?
minus 1?
Oh,
Sorry,
okay.
yeah.
If I hear you clearly, you said, can I clarify where I get the values of YT minus 1, right? You mean how I
Yes.
got the YT? Okay, that's a very good question. Now, this is what happened. I'm actually going to take you initially. This is a model. Can you see the YT right here? That is what you are given, right? Now, if that is a YT, okay, do you know if if I want to get a model for YT minus 1, given the model that I have now? Okay, what is the difference between this guy and this guy? Subtracting 1, right, from t. Then I can write that as 0.8, 0.9. Then I'm going, you know, when I subtract 1 from t minus 1, what does it become? It becomes t minus 2. When I subtract 1 from, you know, that of noise, now, did you see that now? I'm using the knowledge of the fact that if yt equal to this, then yt minus 1 will be equal to that. What did I just did? Subtracting 1 from the subscript. That was what I did. Does that make sense to you now? Did you get that now?
Yes, thank you. That makes sense.
You welcome. Okay, so you have asked a very good question, and you know that depend, you know, getting your yt minus 1 depend on the given model. Okay, now that is what I actually trying to plug in. That is what I'm plugging in for yt minus 1 here. If you take a look at this guy here, okay, I'm actually plugging that for the yt minus 1 that is inside there. Look at that. I'm plugging the whole thing, okay? Now, after plugging the whole thing, now I'm going to use the 0.9 to multiply this guy, 0.9 multiply this guy, 0.9 multiply every time here, right? And you know what? 0.9 times 0.8, that's going to be a constant, right? And when I take if I want to take a correlation, of course, you know, the constant is going to go away. You know, constant cannot, you know, constant value cannot correlate. It is only variable, okay? It's only variable that correlate, okay? So because of that, what I'm going to have now, you know, the whole of this, we actually become correlation. Okay, why do I have a 0.9 square? 0.9 times 0.9. Okay, this one. Then is 0.9 multiplied by this. So I have that one, and I'm bringing this guy here, right? And how do I get 0 here? Don't forget, I said it. You know, the correlation between a noise and a predictor. Okay, this is a predictor. Take a look at that. Okay, because the yt minus 2 is actually, if you take a look at when I was writing the yt minus, you know, model for yt minus 1 the other time, you're going to see for model for yt minus 1, yt minus 2 is going to be a predictor, and therefore here we're seeing this guy as a predictor. And you know what, according to the rule, the correlation between a noise and the predictor have to be 0. That's why you have 0 here. Now this is where we are now. Okay, now that's why we find ourselves here. Okay, see where we are now. Okay, now we are here now, right? We're here now. Now, as we're here now, this is what we're going to do. Okay, this guy here, the whole of this guy here, I'm going to find a correlation between the whole of this guy here and this guy here, and I'm going to find correlation between the whole of this guy here and this guy here. Okay, now if I want to, you know, for the correlation between this guy, okay, and this guy, okay, this is what I have here. Don't forget, 0.9 square is going to come out, right? I'm going to just write correlation between yt minus 2 and yt minus 2. Look at that. Okay. And I'm going to do the same where I actually want to find, okay, the correlation between this guy here and this guy here. Okay. Which is this, which I'm going to bring out 0.9 out. Now, oh my God, take a look at these two. They are the same, right? What is the correlation for the same numbers? They're going to be 1. They're going to be a perfect correlation. Okay. And oh my God, take a look at this. This is a pass noise. If a call a pass values of noise, okay, and this is pass for the time series variable, which is going to be a predictor. You know, this is a predictor. Okay, whether the current value of a noise or a pass value of a noise is going to be a noise. And the correlation between a noise and a predictor, okay, is actually going to be 0. So the whole of this, okay, is going to be 0. That was why you have 0 here. And at the end of the day, oh my God, I got a 0.9 squared. Okay, now if you take a look at this, there's a pattern. You know, we are beginning to see a pattern. Look at that. At lag 1, a 0. We got a 0.9 for the autocorrelation, which is more or less like a 0.9 raised to power 1, right? Now at a lag 2, oh my God, what did we get? 0.9 raised to power 2. Automatically, you can try that. Automatically, looking at this pattern right now, If I want to find the autocorrelation at lag 3, I'm afraid it's going to be 0.9 raised to power 3 with the pattern that I'm seeing now. Okay, here is 0.9 raised to power 1, is 0.9 raised to power 2. Of course, for the lag 3, it's going to be 0.9 raised to power 3. Okay, and because of that, we can generalize for lag k. Okay, and that was why I was asking a question here for lat k. Of course, automatically for lat k, it's going to be rho raised to power k. And don't forget, you know, 0.9 that we got here the other time was a rho. Okay, what that was a rho, right? And then here it is more or less like a rho squared. Okay, and generally at a lat k, it's going to be rho k. Okay, we've generalized. Okay, we've generalized. So take a look at that now. I'm going to stop my share now and I'm going to reshare again. Okay. Do you know, is there anyone who want to ask question about, you know, how I figure out the autocorrelation at like 1, like 2, and the way I generalize? Is there anyone who want to ask question? If you really understand what I just did, I need you to say yes or you comment yes.
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 Okay, thank you so much. And that was why I call this a general. Okay, take a look at that. So by induction now, okay, we're going to say, okay, if anybody asks you to find the autocorrelation at lag 4, okay, at lag 4, it's going to be 0.9 raised to power 4 based on what I have here. Okay, now I want to walk you back to the population model that for autoregressive model or for that one, because we want to have a summary right now. Okay, we want to have a summary right now. Now I wanted to take a look at this now. We want to have a general, want to make a general statement. And the general statement we want to make is, okay, if this is a general form of a model for autoregressive model of order 1, and in a mean form, this is another way we put it. Okay, now what can we say about that based on what we've been doing? You know, we find the mean before, right? Okay, now what I'm trying to tell you now, if you remember yesterday when I was deriving the mean, if you remember yesterday when I was deriving the mean, okay, you know, I got, if you take a look at what I got here, this is more or less telling us is 0.8. What is 0.8? It's trying to tell us our mean is going to be constant. Okay, you know, 0.8 is a constant in the model, right? Constant divided by 1 minus the one that is acting as a slope. Look at that, C1. Okay, if you take a look at the pattern here, because we actually want to generalize for the mean. So which means when you are given any model, a time series model, okay, like this, we want to make a generalization now. Look at our generalization now. You are given this, okay, you are given this. Oh, give me 1 second. You're given this one as an AR or for that one, and they ask you to figure out the expected value of YT. I want to tell you, you don't even need any derivation that I've done before. You don't need to go through all those rigorous things, derivation that I've done to save your time. Okay, the moment you can recognize that this is a formula, the expected value of YT is going to be C naught divided by 1 minus C1. Look at that. That's what you're gonna. That's what you're gonna do to find your mean. Like I said, you don't need to go through all the rigorous one that I was walking you through yesterday, you know. But if you like, there's no problem. If you want to go through all this, there's no problem. But what I'm trying to tell you now, if you look at what we got yesterday, you're going to see that the mean is a ratio of the constant in the model divided by 1 minus the slope. Okay, when you are, you know, as far as the AR of order 1 is concerned. Okay, and that is what I'm trying. That's what I'm trying to showcase right here. Give me 1 second. That's what I'm trying to showcase right here. All you just need to do from the model given, you only need to identify what is your C naught, what is your C1. That's all. Then you solve that, that becomes your mean. Now, when you take a look at the variance, this is the formula. Okay. Now, some of you, if you look at what we did yesterday, I walk you through the rigorous. Look at the formula. You look at what we got. Now, what does that mean? What is 0.19 here? It's 0.19. Okay. is actually the variance of a white noise. Okay, if you go up, look at that. You've been given a white noise follows a normal distribution with a mean 0 and the variance is 0.19. Can you see that now? So which means the variance of the time series yt is the ratio of the variance of a white noise divided by 1 minus what? 1 minus square of the slope. No, 0.9. I mean the rho. Look at that. And that was why we say, okay, you know what? This is going to be the general formula. Look at that. So if I give you a model, a time series model, of autoregressive model of order 1, and I ask you to derive the variance of yt, if you don't want to go by the way I showed you yesterday, if you don't want to waste your time, all you need to do is to make use of this formula right here. Okay, you need to follow so that identify what is the variance of the white noise, and the C1 is actually the regressions, the slope. Okay, take a look at that. And based on what I did today on the autocorrelation, oh my God, if I give you this and I ask you to find autocorrelation at any lag, okay, it is just the ratio, it is just C1, okay, raised to power K, where K is going to be the lag, okay, where K is actually going to be the lag. But there's a condition here. The condition here is that A1, C1, the absolute value of C1 must be less than 1. Okay, this is a condition. Okay, of course, if C1 is equal to 1, let's say C1 equal to 1, what is going to happen? Okay, when the denominator of a fraction is 0, that will be undefined. And that was why we say, okay, it requires the absolute value of C1 have to be less than 1 to be stationary. Is there anyone who want to ask question? Who need clarification? Before I go to the next page, is there anyone? Okay, now, like I said, it will, oh, I think somebody want to talk. Go ahead. Go ahead.
No, I'm good, but thank you.
Oh, okay, you're welcome. Okay, now what I'm trying to say, the absolute value of C1 have to be less than 1 to be stationary. And you know what? Without stationarity condition, we cannot estimate the mean, the variance, and the autocorrelation of the time series. Please take note of this. Every statistical model has assumptions, and this is the assumption for AR1. Okay, because mathematically speaking, if C1 equal to 1, if the denominator of a fraction equal to 1, it's 0, they're going to have an undefined for mean, undefined for variance. Okay, and you're going to have the same thing right here. So what we're trying to talk about is without stationarity condition, then the mean, the variance, and the autocorrelation of the time series will not make sense. In fact, you can't even estimate that. Okay, I want to go, let's say, in multiple linear, in regression analysis, we normally compare models, right? Do you know we can also compare models in time series as well? Okay, take a look at model 1. Maybe if you take a look at what I have here, okay, yesterday I was talking about Kazim's sleeping hours, my sleeping hours, okay, your professor's sleeping hours. Okay, now let's say I'm using a noise model. This is a white noise model, okay, which is the simplest form of a model. I asked a question yesterday whether that really makes sense, because a white noise model actually means you're assuming my sleeping hours is a random variable that it's purely random, that cannot be predicted. That's what the first model is talking about, purely random. Okay, and you know what? The second model said, oh, it can be, there should be a signal in addition to the noise. Okay, what this guy is trying to tell me now, that the numbers of hours I'm actually going to sleep today, the numbers of hours I slept yesterday, play a role in that. That's what this model 2 is talking about. Okay, model 3 is also talking about the same thing, only that the intercept are not the same. But I want to tell you, when you take a look at all these 3 models, okay, if you take a look at all these three models, I want to tell you they have the same mean. The mean is 8. You can prove that. Okay? They have the same mean. They have the same variance. Look at that. But they have different statistical architecture. Take a look at that. But I want to tell you, if you really want to know whether they have the same mean, okay, use the formula here. Okay, use the formula here. You're going to see that will give you 8. C naught, C1, your C naught, okay? In fact, the first one, expected value of YT will be equal to 8 because the expected value of this is going to be 0, right? You know clearly model 1, the mean of the YT is going to be 8. I think you know that. If you take a look at this, okay, if you apply for model 2, okay, if you want to apply C naught, okay, divided by 1 minus C1, okay, you see the formula right here, right? This one, you see that? Okay, now if you plug that in, what is your C naught? Your C naught is actually 0.8 right here. You see that? Okay, divided by 1 minus, what is your C1? 0.9. You do see that? And that is going to be 0.8 divided by 0.1, which is going to be 8. I told you. The mean here is the same thing as the mean here. It's also going to be the same thing as the mean here. You can try that. Now, take a look at all these three models. They got the same mean and they have the same variance. Okay, the three models. Okay, but despite that, despite the fact that they have the same mean, but there's something I want you to see. The variance of the white noise in model 1 is 1. But the variance of white noise in model 2 and model 3 is 0.19. I just wanted to take a look at that. The mean of a white noise in all models, the mean of a white noise in all models is 0, 0, 0. You see that? Okay. Now, when we plot model 1 and model 2, look at what we have. Model 1 is the one in black. Okay. Model 2 is the one in red. Take a look at that. Okay. You see that? That they are not, even though they have the same mean and variance, but the way they actually, exhibit, like the way they play out, the way they spread out is different. Okay, look at that. That's what I wanted to see. You could have two models that have the same mean and variance, but you know what? The way they spread out, okay, may not be the same. Now, when you are that is comparing model 1 and model 2, okay. Now comparing model 1 and model 3, look at that. You see that they have a different trend. Look at that. Take a look at that now. Look at what we have. The pattern is kind of different. They are not superimposed. Okay, they are not exactly the same. Take a look at that. Okay, now looking at the three models, okay, we can actually see that if we try to look at the behavior in terms of whether the one that is most jag or the one that is most smooth, okay, you can actually look at the graph for you to be able to see. But what we can do is when we have some data, okay, if you have data for this, for YT, give me 1 second. Data for YT for model 1, okay, data for YT for model 2, data for YT for model 3. If you have that, I want to tell you, by the time you estimate the parameter, okay, now what I'm trying to talk about is this, okay, how do we fit model to the data? Okay, the model that we have was a population models. All these ones, they are all population models. Okay, now what if you now use the model that we have here to generate a data set, and we now begin to look at what is happening? It's what we can do. Okay, now like I said, in theory this is what we have for autocorrelation, but in practice we're going to collect data set. And we're going to be estimating, look at the curve. We're going to be estimating the autocorrelation. Okay. Now, some of you may be wondering, what is the essence of autocorrelation? Okay. Of course, the essence of getting the autocorrelation at lag 1, at lag 2, at lag 3, up to lag k, okay, is actually to use that to construct an autocorrelation function plot. I'm going to say that again. Now, why do we need to get autocorrelation at lag 1, autocorrelation at lag 2, up to autocorrelation at lag k? Why do we need to do that? Because we need to do that so that will enable us to have Acf plots. Now, my question now is, why do we need Acf plots? Now, let me tell you this. The Acf plots will enable us to identify which of the models, like, I told you we have autoregressive model of order 1. Okay. We also have autoregressive model of order 2. We have autoregressive model of order 3. We have autoregressive model of order 4, and so on like that. And between, how am I going to know? Okay. How am I going to know? And not only that, apart from having autoregressive model, we have a lot of models in time series. We have autoregressive models. We have the moving average models. We have the autoregressive moving average model, which is we call AMA. And we have autoregressive integrated moving average model that we call ARIMA. There's a lot of time series models. But you know what? What is the essence of Acf plots? The Acf plots will enable us to identify, okay, a particular a time series model that's appropriate for our data. Now, let me tell you this. When you plot autocorrelation at lat k against lat k, what am I trying to say? You plot autocorrelation at lat k against, for instance, you plot autocorrelation at lag 1, the value of correlation at lag 1 against lag 1. You plot the values of autocorrelation at lag 2 against lag 2, okay, which is what I'm trying to see right here. That's what we have right here. And what can you see? There's something I want you to take note. Autocorrelation at lag 0 will always be included in an Acf plot. And autocorrelation at lag 0, if you take a look at that, if k equal to 0, okay, if k, for instance, if I want to get the autocorrelation at lag 0, don't forget I'm going to use ratio power 0, is 1. And that is why, if you take a look at this, that corresponds to autocorrelation at lag 0. What I have here is like at lat k, right? And what I have here is the corresponding sample autocorrelation values that we plotted. So what I'm trying to, what you can see right now, this guy here, there's always going to be, it's going to be part of the Acf plots. And that is the autocorrelation at lag 0. Autocorrelation at lag 0 is always going to be 1. Now, if you now start plotting other, if you take a look at this guy now, if you take a look at this guy now, okay, is the autocorrelation sample autocorrelation at lag 1. Sorry, yeah, at lag 1. Okay, this is at lag 0. This is at lag 1, lag 2, lag 3, lag 4, lag 5. Okay, here we are considering up to lag 20. And look at the behavior of the autocorrelation when the lag increases. What happened? When the lag is increasing, what happened to the autocorrelation? Oh my God, it's decreasing. Oh, did you guys get that? Did you guys get that? Oh, can you guys confirm?
Yes.
Okay, thank you so much. Thank you so much. Now, what I'm trying to talk about now is situation where as lag increases, the autocorrelation is going down, is decreasing, then that indicates an autoregressive model of order 1. Some of you may be wondering, okay, we have a code in R that we can use to construct these plots, okay, and we have a code in R that we're going to write that will compute the sample correlation at different lag. But the takeaway from here is when you have an autocorrelation function plot, which is the plot of the autocorrelation against different lag, when you notice that the autocorrelation is decreasing, okay, it's actually going down as the lag, is decreasing as the lag is increasing, then that indicates the appropriateness of autoregressive model of other one. Okay, that's what we mean. Okay, now take a look at another one. This is another model. This is another autocorrelation function derived from another model. Some of you may be wondering, we have some negative values here, we have some positive values, but if you take a look at the one here, right? If you take a look at the one here, they are all positive values, right? They are all positive values, right? For the autocorrelation, okay? And the second one, we can also have situation where we could have a negative value, but the fact remain, take a look at this. Autocorrelation at lag 0 is 1. Look at that. Okay. And what is this? Okay. This is autocorrelation probably at lag 2 or something. Look at that. Because this is 5, right? And you have that, you see going down. Okay. And the way this is going down, if when you take a look at what we have here, okay, and we also take a look at this, you're going to see that this is going down, and look at the negative 2. Look at that. This one is for negative is 0 point. So what I'm trying to tell you now, if this one is autocorrelation at lag 0 is 1, then I'm sorry, at lag 0 is 1, probably autocorrelation at lag 1 is negative is 0.865. Look at that. So from 1 you get to that, okay, and it go up again. So when you have this situation as well, okay, it also indicates ARO of other one. Okay, take a look at that. So situation like this too also indicate that. And that was why I was trying to say, so this is another one. Take a look at that. This is another one. Okay, this is another one. But what can you see here? What you can see here is that after lag 1, okay, after lag 1, all the autocorrelation lies between, probably between these values and that value there, okay, which is more or less very close to 0. Okay, I'm going to tell you the meaning of this. Okay, the autocorrelation function has meaning, okay, which I'm going to tell you, but this is it. Now you're going to see the meaning now. Now, what do we use autocorrelation plot to do? Autocorrelation plot will enable us to identify which of the time series model is appropriate, okay, for the time series data. I'm going to say that again. The autocorrelation plot will enable you to identify, because we have a lot of time series models. How do we know which one is appropriate for my data? Okay. Now, when you take a look at what I have, let's look at the first one. Okay. If you take a look at this, you're going to see that most of the autocorrelation values here, they are within 0. Look at the blue dotted line here and here. You go and look at that. You're going to see that after lag 0, autocorrelation at lag 0 is 1. That one is always 1. But when you take a look at every other one, they're actually within 0. And let me tell you this. If we want to evaluate a time series model, you remember, apart from using autocorrelation function to identify the best model, the best time series model, the appropriate time series model, we also use autocorrelation function plot for evaluation, for time series model evaluation. And let me tell you this. I remember yesterday I was talking about the significance of a white noise model, right? Of a white noise. We have an assumption that a time series error time, the noise in a time series model should behave well, right? Behaving well actually means that it should be a white noise, and being a white noise means the autocorrelation function should be within 0. Look at that. If you take a look at this, all the autocorrelation values at different lag are within 0. Okay, so situation where all autocorrelation values are within 0, then that is definitely going to be a white noise. I'm going to say that again. Situation where the values of autocorrelation at different lag are within 0, because all these guys are within 0. The only one that is not going to be within 0 in any Acf plot is going to be at lag 0. Of course, we don't reckon with that. We reckon with something that starts from lag 1. You know the meaning of lag 0? Lag 0 means now. That's what lag 0 means. No distance. Okay? That we're not interested in that. We're interested in lag 1, at least one distance apart, and so like that. Okay? So autocorrelation close to 0 here means suggests that the model, appropriate model, is a white noise. It's just like what I was showing you the other time about Kazim's model, time series model for sleeping hours. Okay, if the specification of the white noise is to be true, then when I plot autocorrelation function plot, okay, they should all be within 0. That's what we mean. For it to be, for the white noise model to be appropriate. Okay, but when you take a look at this guy here, automatically this cannot be a white noise. Why is it that it cannot be a white noise? Because all the autocorrelation values are not within 0. And what do you see? The autocorrelation values are decaying. They, as lag increases, what happened to them? They are going down. And if they are going down, what does that mean? Oh, if they are going down, and if you take a look at this, the C1, they are all positive, right? The positive, right? Then you are talking about the autoregressive model of other one. Okay, so when you want to assess different kind of models, probably from white noise model to autoregressive model of other one, autoregressive model of other two, and so on to other time series models, you needed to plot an Acf plot. Okay, the behavior of the Acf plot will actually determine the appropriateness, okay, of the model. Now take a look at another one. This one is a series of positive and negative, right? Take a look at that. Okay, series of, when you have a series of positive and negative, okay, where you can see that situation where the autocorrelation value alternates between positive and negative values. Take a look at that. I start with this, I go to negative, now go to positive, now to negative to positive. You can see it's alternating. Then it is still an autoregressive model for that one. Okay, it's still an autoregressive model for that one. Now, is there anyone who need clarification? Because this is very, very important on how I interpret these 3 types of plots. Is there anyone who need clarification?
No, I think I'm good.
Okay. If all of you are good, if you guys are good, I need you to say yes, or you comment yes
Yes.
with my explanation. Okay, thank you so much. And with that, I'm going to complete. I'm going to complete yesterday material, and I'm going to go into today's material. Give me 1 second. Uh, I think there's a supplementary material that I also wanted to see. I'm going to, yeah, there's a supplementary material for yesterday that you can read. I'm going to share that with you. I'll quickly go over that. I needed to confirm if you are actually seeing the complementary material for can you see that? I made a
Yes.
supplementary material. Okay, so because material for yesterday, there are 3 in number. There are 3 in number. This is going to be the 3rd one. Okay, and then this is more or less like a supplementary material. We're still talking about the autoregressive model of other one. Okay, uh, in the outline here, we started what is time series data, and we've talked about some time series graph. Okay, and you know what, this material will give you more explanation uh, to what we've just done. Okay. I told you yesterday, time series data, they are data collected over time. Okay, they are collected over time, and of course, collecting data over time, there's going to be a violation of independent absorption using linear regression, and that was why we don't even think about using linear regression. And you know what? Um, um, we I walk you through what we call a time series plot, a time series graph. If you want to have a plot of the series, you want to know whether it's going to going to have a positive trend or you're going to have a negative trend. Okay, so we can talk about whether it's mean reverting or as explosive behavior, or it has a time trend, or what about seasonality, and what about whether it demonstrates structural breaks. And yesterday I walked you through concept of time series called autocorrelation and stationarity, and I also walked you through the simplest form of a time series model that we call a white noise. And finally we did ARO for the one. But I'm gonna I think I'm showing you this now in case you want to have example of time series data. Okay, you want to get a time series data from economics to social sciences to epidemiology to medicine and physical sciences. I want to tell you on the economy, the gross domestic product, consumer price index, S&P 500 index, and unemployment rate. I want to tell you, if you click here, you're going to have access to that. Okay, U.S. United States GDP from the Federal Reserve economy data. Okay, it's going to be an example of time series. Okay. In social science, if you click here about the population without citizenship from Eurostat, you're going to have, a time series data like birth rate, population, migration data, and political indicators. Okay. For epidemiology, disease rate, mortality rate, mosquito population, you can actually get that from US cancer incident rate from the Center for Disease and Control. Therefore, medicine, going like blood pressure tracking, weight tracking, cholesterol measurement, the heart rate monitoring. If you want to, so and so on like that, you can get that from here. Now, from physical sciences, where you talk about the global temperatures, nowadays people believe there's a climate change. Okay, with the incidents in Europe, in both Germany and Belgium, where flood actually uh, killed a lot of people. Okay, so if you want to know about some global temperatures and the like, you can actually navigate this. Okay, so I'm just giving you example of time series data. Okay, now what is time series graph? If you want to know the pattern, okay, if you want to know the trend in a time series data set, I want to see whether there's going to be appreciable upward movement or downward movement. Of course, the time series graph is a graphical way to do that. Okay, you're going to plot the time series data against time. Okay, so you know what? It's actually we're going to provide us a preliminary tool for detecting. We need to, four of us, have a preliminary investigation for detecting if it is a mean revaling, or it has an explosive behavior. Okay, what of it has a trend, or it has a big seasonality. Okay, and what of it demonstrates a structural break. Okay, and you know what? Uh, with that in turn, we actually we guide the testing, the diagnostics, and the estimation method. Okay, using time series modeling. Okay, in regression analysis, we did the same, where we're trying to make use of a plot. We started by scatter plots, you remember, to residual plots, and so like that. We did all those one before we now, all those actually help us a lot in model evaluation. But I talk about me reverting the other time. Okay, I have a price collected between 1960 to beyond 2010. Okay, this is what we mean by um, mean reverting. Okay, I'm still going to walk you through that as time goes on. And this is when, but if you take a look at this, we're actually fitting the arrow for that too, right? I told you there's a arrow for that one. Okay, if you take a look at it, this is a time trending data. Look at that. It's a time trending because you have an appreciable upward movement. Look at that. You see that now? I'm just trying to show you right now. Okay, this is a this is a seasonality. What do we mean by seasonality? The data said if it exhibits a kind of pattern, okay, and it is predictable, okay, in a time less than 1 year, okay, then you're going to see that if you take a look at that from here, you see the pattern and there's something pick up again and start another. Look at that. So this is more looking like a seasonal time series data. Look at that. Here I'm using the US retail sales in billions of US dollars. Let me tell you an example of a seasonal data is retail price. Retail price used to go up between September and December. I think you know that it's going to increase. Usually you increase between September and December, but between January and February is going to decrease. Okay, so retail price is an example of a seasonal, seasonal data. Okay, now there's something that we call a structural break. This is not good at all for model. I'm going to explain to you right now. Okay, you know, if you look at the pattern from 1960 up to probably 1979. But if you see in 1980, there was a what? There was a jump. Look at that. Okay, that's a break. Okay, there was a jump in 1980. Look at that. Okay, it's only God that knows what happened in that 1980. There was a jump. That's a structural break. Now it maintained the same pattern, and not until if you take a look at probably around look at this one here around 2008. Okay, maybe that is the beginning of the, if you look at it, there was a global financial crisis. Okay, probably in 2010. The beginning of that actually was in 2008. Okay, so when you have a structural breaks, the structural breaks like this is not good for model parameters. Okay, the structural break is going to make model parameter to be unstable, and because of that, that will diminish the capability of the model. We can trust the model, when there's a structural break like this. Okay, the structural break induce what I call non-linearity. Okay, this is an example of a structural break. Okay, it's not good for this. It's not good for a model. Okay, we got to, if you really want to model something, then that exhibit this behavior, then we need to look for more robust time series model. Okay, so this is just a supplementary material to complete yesterday's work. Okay, now I'm going to go into today's work right now. Give me 1 second. Okay, today's work. Okay, today's work is actually, I want to welcome everyone to my lecture today. I'm actually going to call this time series analysis part 3. And here, I want to walk you through autoregressive models. Look at that, autoregressive models. Now, when I say autoregressive model, then I'm actually going to talk about autoregressive model of order 1, order 2, order 3, and so on like that. Then we're going to talk about the Acf plots. I've introduced you to Acf plots. Okay, when you have AR models, okay, when you have AR models, okay, which means you have a lot of AR models. So you need to be able to know which of them will be appropriate. Okay, then we're going to make use of Acf plots. Okay, of course, I showed you the other time. Okay, when the autocorrelation function, okay, decreases exponentially as the lag increases, okay, then that may be the model appropriate, may be autoregressive model for that one. And I also told you we can also use Acf plot to actually identify if a model is a white noise. Okay, now that is what we want to do here. We want to continue from, so this is what I have for you today. Okay, now let us now revisit what we did before on the autoregressive model of order 1. You have a model, this the general form of autoregressive model of order 1. Okay, And this is another way to put that. And you know what? If you take a look at this guy here, okay, it's one of the models that I show you in yesterday's material, which is also an autoregressive model of other one. Okay. Now, if you want to find the mean in this model, okay, you're going to use this formula. Don't forget your C naught is 15.2. Your C1 is negative 0.9. Okay, the mean is going to be 8. The variance is 1 for the model. This is another way to put the model in. If you want to put this one in this form, you need to first find your mean. Okay, your mean is find using this. Okay, so now we've done this before. We're just revising that. Okay, and of course the autocorrelation function, don't forget, in the formula is this. What is C1? The C1 is minus 0.9. Okay, then you're going to put that raised to power k. So which is the autocorrelation function at values at like k. Okay, now for k equal to 0, for k equal to 1, for k equal, you need this guy here. You need this guy here. Give me 1 second. You need this guy here for you to be able to have your Acf plots. Okay, because if you don't have this guy, there's no way you can have your Acf plots. Okay, as even when k equal, of course, when k equal to 0, autocorrelation is going to be 1. I think you know that. When k equal to 1, it's going to be minus 0.9. When k equal to 2, it's going to be 0.81 and so on like that. Okay, and you need those values to be able to get your Acf plots. Okay, you guys confirm again if you guys are hearing me clearly.
Yes.
Okay, thank you so much. Thank you for confirming that. Okay, the next thing I want to walk you through now, we needed some data. Okay, we needed data set. We actually want to simulate. My TA is going to walk you through how to simulate, or even though I'm going to provide some code for you today as well. Now, because you have been given the population model, okay, we can actually simulate some data for YT. Don't forget, which distribution am I going to simulate from? Of course, I'll first simulate for WT, noise. Don't forget the noise. If I want to simulate data for noise, okay, I'm actually going to simulate from normal distribution with mean 0. I'm going to specify mean equal to 0 and variance equal to that. And the moment I have the noise data, okay, the moment I have the noise data, then I'm actually going to have YT. Okay, now I'm going to walk you through the process of doing that. Now, this is the code. Now, I want to show you now the code in R. Okay, if you for instance, I want to simulate 1,000 data set based on that model. Okay, why am I setting seed? Because if you don't set seed, the 1,000 data sets you're going to generate will be different from mine. Okay, but when we say set dot seed equal to 2, if everybody sets seed equal to 2, we're actually going to have the same data set that will be generated. Don't forget, we are generating the 1,000 data set from the randomly. Okay, and this is just for reproducibility. Okay, what is the code in R? If I want to do that, the YT, the data set I want to generate for Y, I'm going to arima.sim. Look at that. Simulation. That's what it means. Arima.sim. If you copy the whole of this into R, okay, if you copy the whole of this code into R, you can try it. Okay. And after doing that, you write YT and you click on enter. You're going to have the 1,000 data set that I talk about. Okay. Now, when you have your 1,000, why are you specifying this? Okay, because the model, you need to see a model, you need to see a population model before you know what to write as a coefficient for the autoregressive model. Take a look at that. In the model, you've been given that is minus 0.9. Okay, minus 0.9. You've been given, you're going to be given the model, okay, before you can simulate, right? Okay, so you're going to indicate that. That's what I'm indicating right here. Then the standard deviation, of course, is going to be the square root of variance. Variance of what? Don't forget the variance of the white noise. Okay, you've been given that the white noise has the variance of 0.19, right? Take a look at that. Or what you're just going to do, then in the code, you're going to add 8 to that. Where am I getting my 8 from? Oh my God. Where am I getting my 8 from? Of course, 8 is the mean of this model. Don't forget, I've been able to find that. Expected value of yt equal to 8, right? Okay, so and then I'm going to plug that in. Okay, I'll give me 1 second. I'm going to plug that in. Okay, now this is the entire code. Look at that. That's the entire code. Okay, now I'm going to have, give me 1 second. I'm going to do something now. If I copy all of that, let's copy that. Okay, and I'm going to share my R interface right now. Give me 1 second. I'm actually gonna um I'm gonna do that right away. Give me 1 second. I'm gonna share my R interface. Well, I'm gonna copy that into R, and you're actually gonna see what I'm gonna have. Okay, so I just want to show you that how you can simulate. Okay, so give me 1 second. I'm gonna share my R interface, and I need you to confirm if you are seeing my arrow interface. Are you guys seeing my arrow interface? Can you confirm if you're seeing my
Yep.
arrow interface? Okay, thank you so much. Then I paste that. Okay, I paste that right now. Take a look at that. If I click on enter, okay, and I click on YT, enter. Oh my God, confirm if you are seeing my data set right now. I got 1,000 data set. Confirm if you're seeing that. Are you seeing that?
Yes.
Okay, this is a simple code. You don't need to load any package. Okay, you don't need to load any package. Okay, you actually, I told you the essence of setting the seed. If you write set dot seed and you put 2, it's gonna be this same data set that you're gonna have. But if you don't set your seed, the data set you're gonna have will be different from mine. Okay, so take a look at that. That's gonna be easy. Okay, we're gonna come back to that. I want to go back into my material right now. I'm going to go back into the lecture material right now. Give me 1 second. Now you know how to do that. Okay, so now we've been able to simulate the data, right? For YT, the 1,000 data set, using the information provided. Okay, excuse me. So we'll be able to do that. Now the next thing now, how are we going to have a plot? Now this is a code. If you write this code, okay, what do you want to plot? Plot.tx, tx, okay, yt, okay, you've already, this is what you're actually going to have. Okay, this is what you're going to have. Take a look at that. Okay, so that is the code. That is for time series plots. Okay, just see that now. That is the code. Okay, now do you know we can do a lot on the variable that we simulated? Okay, how do we find the mean of the data set we simulated? The mean is yt, mean of going to write mean yt, then how do we find the variance? Okay, now if I go back into my R right now, give me 1 second. Okay, and I want to find the mean of my simulated, okay, my simulated data set. I'm actually going to do that, mean into that. Okay, I got the mean to be 8.013084, but you know the other time, the mean, what is the population mean of the model? You know, the population mean of the model was 8. Okay, but what is the sample mean now of, the sample mean, the mean we obtain from the simulated data set is actually 8.01304. They are not the same, but they are very close. The population mean and the sample mean, they are not going to be the same. Take a look at that. Now, if I want to find the variance right now, okay, the variance of YT, okay, it's actually there. Look at that, 1.076887. Take a look at that. Okay, Now, I'm going to go back to my share. I'm going to go back to my slide. Now you can see now, that was how we got the mean to be that, the variance to be that. Okay. But you know what? The true values of the mean and variance was 8 and 1. You remember? The population mean specify, the one we determine using the formula here, the mean was 8. The variance was 1. Those are the true values of the mean. But from the data set that we have right now, look at that is the mean and the variance that we got. Okay? And that is expected. Okay? Because of the sampling error. That's expected. Okay? Now, and that was why I said, are these estimated values close to the true values? I'm going to say yes. Because 8.01304 is close to 8 and 1.076887 is close to 1 in a way. Okay. Now, if you want to find the autocorrelation, I told you the other time that how are you going to find the autocorrelation function plot? You need the autocorrelation function plot to be able to decide on the appropriate model for time series. Okay, in R, how are you going to do that? The moment you have your data, it's going to be a CF of that data. Okay, let's go there. Okay, let's go there now. So I'm gonna show you my R now. Okay, that is my R, right? Okay, so I'm gonna write ACF. Okay, ACF. Okay, into YT. Okay, then I'm gonna click enter. Oh my God, can you guys confirm this? Did you confirm the ACF plot that I have right now? Can you confirm that?
Yep.
Okay, thank you so much. Now, what did you see? Oh, you're going to see the positive autocorrelation and the negative autocorrelation value are alternating, right? They are alternating. Alternating me, oh, I got a positive followed by negative, positive. So you know what that means, okay? So it's just easy that way. Oh my God, this is so easy. Okay, and that is what I have. Okay, that's exactly what I have right here, right? Is that not what I have? Okay, now I told you what the first one is. This is autocorrelation at lag 0. Autocorrelation at lag 0 is always going to be included in the autocorrelation function plot. And of course, it's 1. Okay, take a look at all of that. That's what you have right now. Take a look at them. Okay, and you know what? Take a look at this guy here. This guy here is row 1. If this is row 0, this is row 1. Okay, this is row 2, and you know the meaning of row 1, right? Okay, 1 distance apart. Okay, the correlation between the current value and the past value. Okay, and that is on the negative side, right? That's 0.907. Okay, and this guy here is row 2. Okay, that is the value there. Okay, so this is if this is row 2, you have row 3 and so on like that. Take a look at that. Now the question now is, what does the blue dotted line implies? Take a look at the blue dotted line. Okay, now the blue lines are the 5% significance limit for testing the autocorrelations equal to 0. Okay, um let me tell you this. If all of the correlation values lie between the blue dotted line, that will indicate a white noise model, right? But I want to tell you, it is not all the time. We're gonna leave a room for error as well. Okay, because there's possibility if I have 100% of this, and if 95% fall within the blue dotted line, I'm still fine. I'm still okay. Okay, for it to be a white noise, because there's going to be room for error too. It is not until all the autocorrelation values lie within the blue dotted line before you can conclude that it's a white noise model. Okay, so that is what we mean. Okay, but when you take a look, and I told you autocorrelation at lag 0 is always going to be 1. I think I told you. Okay, I told you, right? Okay, now if you want to read out the values. Can you give me 1 second? 1 second. Just give me 1 second. Thank you so much. Just give me 1 second. Okay. Can you guys confirm if you guys are hearing me clearly?
Yep.
Okay, thank you so much. Now, this is the values. If you take a look at these values, we actually extracted them from the, from here, right? So we extracted them from here, and these are the values right here. Okay, you can see it's alternating between positive and negative, right? And when it is alternating like that, that is an indication that the model is actually going to be a error for that one. Okay, I told you before, that is how we identify a time series model to be error for that one. Okay, and another thing I wanted to take note from the population, from the formula we have done before. Okay, we have the formula to be minus 0.9 raised to power k, right? From the formula of autocorrelation. Okay, now the one I have here, the value that I have here is the sample autocorrelation, or we call that estimated autocorrelation. We got this one from the simulated data. But do you know you can have a way to compare the one you got from the simulated data with the one that we can compute using this? I know some of you may be wondering. Okay, and let me tell you this. The one that you're going to compute through this is going to be true values. Okay, but you know what? We can have a way to compare the one we estimate from the simulated data set to the one that we compute through this. And I told you the one you're going to compute through this is the one that is have a true value. Okay, now let's see that. Okay, at lat k equal to 1, if you plug in, going to have this. So if you plug in 2, going to have this. Plug in 3, up to you get to plug in 7. Now, this guy here, give me 1 second now. This guy here, they are the true value of the autocorrelation. Okay, and why this one are the estimated, the one from the sample, and the one from that we compute using the formula which we call the true values. Now let's now compare them. Okay, we want to compare them. Look at that. You start comparing them now. Okay, then you're going to see they are very close, right? They're very close to each other, right? So what I'm just trying to let you know here is just that to let you know how the difference between there's a difference between estimated autocorrelation values at different lag and the true values. Take a look at that. Okay, now having know that, the next thing we want to do now from a data set, can we have a way to estimate parameter of autoregressive model of other one? Okay, I'm going to walk you back. You're going to see something right now. Okay, I'm going to show you something now. Now, if you look at the population model that you are given, we already have the intercept to be this. We have, the road, the slope to be this, right? These are true values, right? These are true values. But you know what? can we have a way to estimate these values, okay, these values from the data set, so that when we estimate that from the data set, that we're going to compare those values that we estimate from the data set, to the true values. Okay, that's what we want to do right now. And now the question now is, how do we do that in R? Oh my God, that is going to be so easy to do in R. And I'm going to show you the code right now. Okay, now what we want to do now is, how do we fit autoregressive model of order one to data set? Okay, if you want to do that in R, this is how you're going to do that. You're going to write this equal to ARIMA. Okay, ARIMA, ARIMA here is AR means autoregressive model. Okay, I is the difference. MA is the moving average model, because we have different kind of models. Now, this is the code. Okay, now this code now is for AR1. Okay, if you look at what I have here, the first part is for AR, the second part is for difference, which we call the order, and the third one is MA models. But right now, when I'm trying to say in ARIMA, okay, this one means, oh, I'm not interested in moving average. Oh, this one say, oh, I'm not interested in in the differencing. Okay, and I'm interested in this one. Having a value here means, oh, I'm interested in autoregressive, and indicating one means, oh, I'm interested in autoregressive model of order one. Okay, so when you see 100, that is autoregressive model of order one. When you see 200, that is autoregressive model of order two. When you see 300, that will be autoregressive model of order three. When you see 110, 110, for instance, if I have 110, that would be autoregressive autoregressive model of order one integrated at one. Okay, and I'm not considering moving average. Okay, so I just wanted to take a look at what I have right now. This is going to be the code in R. Okay, like I said, the ARIMA that we're using has an AR part and the MA part and the difference parts. But right now, we're focusing on autoregressive model of order one, right? Okay, now if I copy ARIMA, if I copy that into if I copy this guy here, okay, let's copy that into R, and let's see what we're going to have. Okay, you're going to see what we're going to have right now. So I'm going to share my R. I'm going to share my R interface. Okay, now I copy that. Okay, then I click on enter. It's running. Then I mode. Okay, take a look at what I have. Or I actually gonna put summary. Let me see. If I put summary into YT. Okay, now if you take a look at this, you don't need to put summary into YT, otherwise you're gonna just talking about the script status or YT. But you know what? Just put mode, enter. Now look at what we have. Now we have two parts, which I'm gonna tell you right now. This side is the slope. Okay, this is the intercept. Okay, and 0.0133 is the standard error of this estimate. 0.0072 is the standard error of that. Now, what can you see now? Okay, this is our C0. The intercept is that, and the intercept is always going to be the mean for AR1. Okay, now take a look at what I'm trying to show you, or what I'm trying to tell you right now. Okay, this is C0 and this is C1. Okay, now let me now take you back to the regression, to the lecture slide. Then you're gonna see for yourself what I mean. Okay, now, like I said, this is the way the output is gonna look like. Okay, these are the estimate. This is for the intercept, and this is for the row. Okay, minus 0.9066. And these are the standard error. And this is the variance of the entire model. This is the log likelihood, and this is the AIC. Okay. Now, this guy here, the sigma squared estimated as this. Okay, the sigma squared, don't forget the sigma squared. Give me 1 second. The sigma squared is actually is the estimated variance for the white noise. Okay, is the estimated variance for the white noise. Okay, now look at what we got right now. Okay, now when you compare the parameter, when you compare the estimate of the parameter with the one that was specified before, okay, you're actually going to see the difference. Okay, so what I'm trying to tell you now, the intercept that we got, I told you the intercept that we got in AR1 is the mean. Okay, is the mean, is the same thing as the mean of the time series model. Okay, take note of that. Now, based on what we've done, if I now want to write the model out, the fitted model, like I have a time series output right now, and I want to write the fitted model, or what I just need to do, what is my mu cap? Take note, your mu cap is always going to be the intercept that comes from the output. Okay, to 2 decimal here, that's what you see, right? And what is your C1? Is this guy here. Look at that. Okay, now what I'm trying to tell you now, okay, this is the fitted model. Okay, so, and this is another way to put that. Okay, is there anyone want to ask question on the fitted model? Now, if you take a look at this fitted model now, if you compare this guy now with the population model, the C naught here is 15.30. What do we have? What do we have in the population model? Let's go. You're going to see what we have in the population model. You're going to see what we have in the population model now. Now, in the population model, it was 15.2. Can you see that? But when you look at the slope, you're going to see that the slope are more or less the same. Okay, to 2 decimal, it's going to be minus 0.91, right? But why the other one was minus 0.9? So kind of very close. Look at that. Okay. Now, the last thing I'm going to walk you through today is what we call model diagnostics. How do we evaluate time series model? What I just walk you through now, how do we identify, how do we estimate parameter in an autoregressive model for that one? I've walked you through that. And I've also walked you through, okay, how to generate time series data, okay, and how to be able to compute some descriptive statistics and stuff like that. Then I also walk you through how to obtain the autocorrelation function plots, okay, that will enable you to identify the appropriate model, time series model. But you know what we want to do right now? We want to do model diagnostics, okay? If our model fits data well, what do we expect? How do we know our model fits the data well? That the residual should behave like a white noise. Okay? What do we mean? For residual to behave like a white noise, that is synonymous with what we did in a linear regression, where we expect the unexplained variation to be the effect of the unexplained to be very, very small. Okay? And in other words, in time series analysis, there should be no signal left in the residuals. Okay? There should be no signal left in the residual, because we are looking at the situation, because the data set that we have, the time series data set that we have is contaminated. It's a combination of a signal and the residual. And our effort here is to filter out the residual from the, to filter out the signal from the residual. And if I'm able to figure out the signal from the residual, then we're going to say our white noise. I mean, the residual behave like a white noise. Okay, residual behaving like a white noise means it's well behaved. And let me tell you this. How am I going to know? Oh my God. What I'm going to know, I've already footed a model before, right? Okay. All what you need to do is to plot mode $ residuals, where your Y lab is residuals. Okay. This is more or less like very similar to what we did in linear regression when we were trying to, conduct a residual plot, when we constructed a residual plot. Okay. Now, this is more or less the same as that. Okay. So right now, what I expect to see, I expect all of this to be within zero. Okay. I expect all of that to be, most of them to be within zero. The moment the autocorrelation values at different lag, at different time are within zero. What does that mean? Okay. If they're within zero on average, let me say within zero on average. Okay. Then that is going to be a good model. Okay. Now, and that was what I said. Okay. And that's what you're going to see right here. That's what you're going to see right here. Now take a look at that. Okay. So, what I have here is just the time plot of the residuals, just like similar to the one you have in the regression analysis. Okay. We want to see whether the average of residual is zero. You remember that is also what we want to do too, what we did too in linear regression. Okay. Okay. That was why I said, if you take a look at this guy now, the averages of the residuals are approximately zero. I'm talking about average, on average. What about the variability? Okay. The variability is the same. It does not change. This constant variance over time. Okay. And those are the two properties that we see now. They are actually consistent with the property of a noise. But if you want to see the clear picture, you know what you're going to do? Go ahead and find the construct the autocorrelation function plot of the moded $ residual. Mode, don't forget my mode. That was the model, right? I'm going to show you now. That was the code that I used in my model. I said mode equal to the model. Look at that. Mode equal to that, right? Okay. Now, let's look at the Acf plot. Oh my God. Take a look at my Acf plot. Now you're going to see all virtually, in fact, all the autocorrelation function values are within the blue dotted line. They are within zero. That's what it means. Okay, except autocorrelation at lag zero. I told you. Okay, that is not what we're not interested in that. This is normal. Autocorrelation at lag zero is always one. So it should be the only one that should be outside. Okay. But you can see every other one is within zero. Then what does that mean? That it means the residual actually behave well. The residual is behaving like a white noise. Okay, that is what it means. It means we have succeeded in filtering out the signal from the residual, separating the signal from the residual. That's exactly what we've done. And that was why I said, the lag beyond zero, I've estimated autocorrelation value approximately zero. Take a look at that. Take a look at them now. Okay, I told you yesterday we use autocorrelation. I told you yesterday that one of the significance of a white noise, we use it in model diagnostics. Now, in model diagnostics right now, where you can see the behavior of the autocorrelation function, and of course, for model to behave well, okay, for a time series model to be reliable, for a time series model to be adequate, then we expect the autocorrelation function of the residual. I'm going to say that again. We expect the autocorrelation function of residual to behave this way, where all the values are actually going to be within zero. Okay, and that shows the model is really performing. Now, I'm going to go through an example right now of a Google stock price. Okay, where we're using adjusted daily price right here, the closing price between April 22, 2018 and April 22, 2019. Okay, and we call that variable GOOG. Okay, when you 404 starts by having a preliminary investigation about how the trend of that series is going to be. This is it. This is a time series plot. If you have the access to the data set now and you plot you have a time series plot of it, this is what it's going to show. Look at that. It's going up, going down, and later go up again. Look at that. And if you want to get the ACF plot of it, now let me tell you, we have two different kind of ACF plots. Okay, we have two different kind of ACF plots. We have an ACF plot that will tell us, that we use to determine the appropriateness of a time series model. Okay, whether to identify a time series model, we have an ACF plot that we use in that regard. And we have another ACF plot that we normally construct on residual. And that one will help us to, that one will enable us to know how adequate is a model. Okay, and if you want to test the adequacy of a time series model, and that depends on whether the residual is a white noise. Okay, now the one I'm trying to showcase right now, we are just trying to construct the ACF of the data, is just to be able to tell me whether it's going to be ARO for that one or a different model. Okay, and what can you see right now? You can actually see that at different, as the lag is increasing, what happened to the autocorrelation value is going down, and that will mean, as far as the Google price data is concerned, it could be ARO for that one. Okay, that's what we mean. It could be ARO for that one. Okay, now that's what we mean. Okay, now if we now decide, since we've been able to see from the autocorrelation plot, because of the fact that the autocorrelation value is going down when the lag increases, we are suspecting ARO for that one. Suspecting ARO of other one, what we now need to do, we can now fit ARO of other one to the data. Okay, look at what we're doing. Okay, we now want to feed that now. Okay, want to feed the arrow for that one. This is 100. Look at that. This is the data, and this is what we have. Now, fitting the arrow for that one. Okay, you see what we have. Okay, this is a fitted model. What we're trying to say, the Google price, okay, at a particular day, okay, actually depends on the previous day. That's what we mean, right? Okay, how good is this model? Okay, suspecting an ARO for that one using autocorrelation function plot, okay, it is not enough to say that it's actually going to be ARO for that one. But you know what we can do? Okay, we can now try to look at the model diagnostics and be able to see whether it is truly ARO for that one. The way we're going to do, then we're going to do what we did before, right? We get a plot of the model $ residual to see whether the mean over time is going to be 0 and the variance, whether it's not going to change over time. And not only that, we're going to construct the autocorrelation function for the residual and be able to investigate whether the autocorrelation function of the residual, whether they're actually going to be within the blue dotted line, whether they're going to fall within 0. Take a look at that. But I wanted to see at like 10, that is kind of coming out, right? At like probably 23. But the fact that we have 2 points coming out of that, the majority of them is still within. Like I told you the other time, we're going to allow room for error, right? Don't forget we're using 5%, provided if the number that is out, okay, that is outside that is within 5% of the whole thing, we are fine. Because don't forget, and that was why I said it right here. I said, based on the autocorrelation function plot, most of the estimated autocorrelation are close to 0, most of them, except the one at like 10, at like 23. Okay, so the estimated autocorrelation at like 10 and like 23 exceed the boundary we know, and which means that these are significantly different from 0, right? at 5%. Okay, but you know what? Since the significance level is 5%, we expect that approximately 5% of the bars will exceed, okay, the boundaries, even if the autocorrelation is equal to 0. Okay, and that's why I said among the 23 bars from lag 1 to 23, we expect that 1.15, that is 23 times 0.05 bar, exceed the boundaries. So we have 2, and this is not far from the expectation of 1.15. So we can conclude that the residual behave like a white noise. Okay, we can still make that conclusion. Okay, because we have given room for error. Okay, the residual behave like a white noise means, oh, the model we suggested is actually appropriate. That's what we mean. Okay, and for the forecast, I think I'm going to stop here today because this is 106. I'm going to continue from the forecast tomorrow. How we're going to use our model to make a forecast, because the essence of fitting a time series model is how we can actually understand the variation in the past and now to predict the future. Okay, but you know what? That's where I'm going to start tomorrow. How do we predict using a time series model? But what we have done today, I think I've walked you through. Let me have a recap on what we've done today. Today, I introduced you to ARO for the one. And of course, I walk you through the theoretical way of deriving the mean, the variance, and the autocorrelation at lat K for a given autoregressive model of order one. Then I also walk you through how to simulate data set, okay, from a particular distribution, for time series data, right? And from there, I also walk you through how to estimate the mean, the variance, and the autocorrelation at lat K. And that also gives us opportunity to compare the population autocorrelation values with the estimated autocorrelation values, and we can see that they are very, very close. And not only that, I also walk you through how to estimate parameters, okay, using R of the autoregressive model of order one. And that gives us opportunity as well to compare the estimate of the parameter of the model with the true values that we started with. And of course, we saw that they are very, very close as well. And the last thing that we did was that I actually, um, walk you through the idea of autocorrelation function plots. The autocorrelation function plot can be used for two things. Number one, the autocorrelation function plot can be used to identify which of the time series model is actually going to be appropriate. And lastly, the autocorrelation function plot can also be used for model diagnostics. Okay, we're going to do the autocorrelation function plot of residual, and we want to see the expectation is that the majority of the autocorrelation values should actually be within 0. And the moment the majority of the autocorrelation values are within 0, then what are we trying to say? Then what we are trying to say is that the residual in the time series model behave well. And you know what? For a time series model to do a good job, okay, for a time series model to do a good job, the residual have to behave well. It means that is the residual has to be white noise, okay. And of course, I think I've shown you using autocorrelation function plot. And finally, I think I walk you through an example using the adjusted closing price, okay, the Google price, okay. And we started by having the time series plots of the model. We saw the trend, and from there we plotted an autocorrelation function plot for us to be able to see to suggest a model that we can use. And in that situation, we saw that the autocorrelation function plot is actually decreasing as the lag is going. I mean, as the lag is increasing, and that suggests ARO for that one. And when we fitted ARO of order one, okay, we carry out the diagnostic testing again by trying to obtain the autocorrelation function plot for the residual. And we found that most of the autocorrelation values actually lie within 0, and which suggests the residual behave like a white noise, and that confirm the appropriateness of the autoregressive model of order 1. Okay, for that. So what we're going to continue. What we're going to do, what we're going to start from tomorrow is how we can make a prediction using a time series model. Okay, is there anyone want to ask question before I go today? Is there anyone?
I'm good.
Oh, okay, thank you so much. Now, if you guys are good with my explanation today, with I need you to comment yes or you say yes.
Yep.
Yes.
But you know what? If thank you so much. Thank you so much. And you know what? If any one of you need clarification, of course, you can actually send a message to me and you meet with me. Okay, I want to appreciate everyone who have attended my lecture today. I hope you guys enjoying it. Until tomorrow, that I'm actually going to come your way with another exciting topic in statistics. Of course, tomorrow we're going to start with the forecasting. Okay, we're going to start with how to predict from a time series model. Okay, that's what we're going to start from tomorrow. Make sure you guys stay safe and have a good day. Bye for now, guys.
Thank you. Bye.
Bye. Thank you.
Bye. Yeah, you're welcome. You're welcome. Yep.